Well, g'day guys. A quick recording because I'm not going to be with you during this week in term 3. I'm actually taking some leave, but I wanted to make sure you got to hear this from me. So a quick teaching video. Now you can see my face. Look at that. Maybe that makes the video worse. I can't tell. I want to talk quickly about a topic which we don't spend much time on in the syllabus. It's actually about the way images are formed in lenses. We do mirrors as well, but mirrors will be covered while I'm away in class, but lenses is a bit particular. In all the questions that I've seen so far in the prelim exams, just for a bit of context, there's not a lot of questions that have asked specifically for you to conduct a detailed description of how lenses transform images or magnification. But technically the syllabus says to cover it, but it's not very specific how. It's very typical of this new syllabus. Cover things, but doesn't give us very specific cases. Last year's prelim final, for example, one of the questions was about how images form in mirrors. So there was a spoon. One side of the spoon was concave, so the inside eating side of the spoon, concave, and it showed an image of a face reflecting. And then the other side, the convex side of the same spoon, and it showed the reflected face of somebody in the outside of the spoon and the inside, and you had to draw a formation of an image in the mirror. So one of the mirrors formed an image close to the mirror, so that is the image actually shrunk from the person's size of their face, right? The light shrinks because it converges in front of the mirror. And the other one, the convex outside curve, shows the face larger. So the image is actually forming further back away from further back from the reflecting surface, and it's actually a virtual image. And you had to account for that, describe. See, but it didn't involve lenses. So lenses can be a little bit more tricky for some people. They find it that way. So we'll cover it briefly in this video. And I've given you, in this whiteboard presentation I'm about to show you, I've actually given you a past prelim examination question you can work on by yourselves. Okay, so moving off to the whiteboard now. We've got, this thing is about lens focal length and lens magnification power. So these are the terms you need to understand about talking about lenses. We're always talking, just like we are with mirrors, about different shapes. So you've got convex shapes like that, curved outside with light rays hitting them. Sorry, the pen's a bit manky, right? Or you've got concave shapes with light coming in and hitting those mirrors. Remember, of course, in this light as a ray topic, we're representing light with these rays, but remember that ray is just a diagram. It's like a vector arrow. It's not meant to be a true representation of light. Light actually spreads out in all directions, but it can travel forwards in a wave form. So light has a wave nature as well as a particle nature, but a wave nature. And so we regard the wave as if it were traveling forwards along a straight line like this and like this, but it's just an approximation. Okay, so take a quick look at waves. For a thin double convex lens, so when we say thin, this word thin, I want to make clear why we bother with that word. The reason is because if you look at, let's say this lens down here, this one here that I'm selecting right now. Now you look at it, what we tend to do in physics is speak about lenses being thin glass. Now, you know that when light comes along here and it enters, it's coming along, if light enters into a bit of glass right there, you know that it begins to bend, right? It bends within, and then it should bend again on leaving the glass, right? Now, the reason we talk about thin lenses is because we want to make the lenses do the bending effect, that is to create images of different sizes or magnified or shrunk sizes, but we don't want much of that effect to happen within the glass, right? Because if the glass is long, if the longer the piece of glass is, then there's going to be more refraction effects. So we tend to speak in physics of them being thin lenses, and we tend to disregard the effect of light refracting from air to glass and glass to air again, okay? There is an effect, but the glass is so thin, we disregard it. It's a bit like friction, right? In doing dynamics, you know, balls roll down ramps, they encounter air friction and rolling friction. There is enough, it makes a difference, but we're allowed to calculate as if it doesn't exist. Think of refraction inside the glass of a lens. It's so thin, a slice, we pretend it doesn't exist. Okay, so what is a double convex lens? So it's like this, right? Double convex or biconvex, we'd call that, right? Biconvex lens here has got simply two outward shaping faces. So outward facing curves, right? So kind of like a giant eye turned on its side, convex and convex, right? Biconvex. Now the kind of lens that is actually over here. It's actually a converging lens. Converging, why? Because the refraction on those lenses, when the light leaves this curved, bent, convex surface, it actually refracts and focuses the rays together into one point. And that's actually here called the principal focal point. Okay, so that's a very unique thing about biconvex lenses. They are converging, a converging lens, right? And in particular, they bring an image. They bring an image to one point, one very focused point on the metal. Sorry, in front of the lens. Usually the opposite side of the lens to where the light's coming in, although that can vary as well. So now, what are some of the key terms? This one's an important one. I'll move this up a little bit so you can see. What's the principal focal length? Okay, principal focal length here is this thing down here, right? Difference between the middle of the lens, the distance between the middle of the lens and the focus, the place where all the light rays focus. That's called focal length, and we always call it F. So you can see it written right there, that's F, okay? Principal focal length of the lens, it's probably the most important thing about a lens. Now, what if you want to do some maths with that lens? Okay, so some maths you can do with a converging lens. Focal length, let's say it's like on this lens here, biconvex, the light is going to come in and bend, it's converging, so it creates a real image here where the light rays converge. So that's a bit like spectacles, right? The ones I'm wearing right now. And some camera lenses too. Focal length 20 centimeters. The power of a lens is given in P. Now, if you're a optometrist, you use the word diopter, but we're happy to just use magnification power because we're not optometrists. But diopters is the way they describe it. But if I have a focal length of 20, the power is just 1 over the focal length. So convert 20 centimeters to 0.2 meters, 1 over 0.2, it's got a lens power of 5. Okay, so a lens power, a focusing power of 5, and optometrists would use that to design glasses. Okay, let's zoom ourselves back out for the picture. Now, you've had a good look at converging lenses. Makes sense that we should know about diverging lenses too, right? So what's a diverging lens? Well, it makes pretty good sense if you look at it right here. What if you've got a double concave lens, right? So concave meaning, biconcave meaning two inward focused two inward curved surfaces for the glass. Again, it's thin, so we can disregard the effect of the glass refracting the light. As light comes into glass and out of glass, we'll disregard the effect because it's thin. Principal focal length is the same, but this time the waves of light are getting back projected. So we're coming in here, right? So we're coming in this way, and the lens is actually pushing the light outwards, right? That's why it's called a diverging lens, and the light rays are getting distributed out this way. It's diverging, that is coming away. Now, a diverging lens cannot make a real image. It can't make a real image, that's thing number one. It can only make what we call virtual images. That is, it'll form an image at a certain place for our eye to see, but it is not the result of light converging into one place. It's actually sort of an optical illusion. It's called a virtual image. And over here, the back projected rays would come together, and that focal length is given a negative sign. So that's important, right? So if you're doing a little calculation or two with that, you've got to use the negative sign. Okay, so what about over here. For example, if it was the same size as the other lens example, 20 centimeters, 0.2 meters, I go 1 over negative 0.2, okay? Because the virtual image I'm going to see back here is actually behind the lens. The lens is diverging light out to there, but I trace back, look at these dotted lines. I would trace back from where those lens spots are. I'll trace back, and it's called ray tracing. If I use maybe different color pen or just dotted lines with a ruler lined up along here, I trace back, dot, 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 and I trace back each one of these focal diffracted rays, and look, it ends up converging on the front of the lens. In other words, it's as if you're seeing it in front of the lens, but you're not. You're actually seeing a virtual image, a fake image of it, as if it was in front of the lens. Okay, very important you put that negative sign in there for those. All right, so it'd be -5 would be the power of that lens. -5 because it's a diverging lens and I'm looking at a fake image or virtual image. Principal focus of a lens, well, what affects it? 3 things. So the textbooks, that's where I got this information from. The principal focal length is determined by what's the index of refraction in the glass. So that can vary depending with quality and, well, usually the density of the glass, right? So some glasses are optically dense, a lot of molecules cross-linked in there. Some are not very dense. So what is the index of refraction? Remember, refraction indexes are given in terms of N, right? So I can compare different glasses, N1, N2, etc. And I might have a particular preference. And if you're an optometrist, you design lenses like this to specifically fit the needs and the kind of magnification. They know all about that. That's their expertise. Okay, second factor is the radii of curvature. So how round, think about a pair of glasses and how round they've got to be, right? And then the medium in which the lens is residing. So if it's just in air, well, of course, remember refraction through air is going to be different as the light leaves glass. Of a certain curvature, it'll refract a certain amount depending if it's going into air or somewhere else. So there might be some applications. For example, underwater cameras, different formula, right? Because they're refracting light out from the glass lens straight into water. And water does not have the same refractive index as air. Okay, you can actually calculate it, and the optometrists use this thing called the lens maker's formula. All right, now, before we move on to the very last part, which is angular magnification, I wanted to quickly show you those 3 little things. So the factors, index of refraction, the radii of curvature, and the medium. Have a look at those in action, as if we were in the lab, perhaps. Let's try that. So what I'll do, I'll just flick you back over to a couple of images that show that. If we had a light ray kit out, we would have this displaying in a dark room with some light slits coming out of those black plastic slits with 3, and we're actually going to deliberately use 3 parallel rays of light, and that's one of the ways we describe light going through a lens. Okay, so take a look with me at these couple. First of all, this one, obviously, what kind of lens is this? Obviously, biconvex, you can see. So biconvex is a converging lens. So can you see the light is coming in, 3 parallel slits. Do you notice there's all these little faint ones coming over here? You should know by now immediately, this is a Perspex lens with the refractive index not very high. Look what's happening. Some light is passing straight through and it's refracting according to the factors. But what are these light ones back here? Well, that's light reflecting. Remember, light can reflect and refract. It can be split unequally. So, you know, some of the aspects of the light transmit through, but a light of lower intensity is reflected back. So some of the light is going to be pushed back depending on the energy of those photons. But here you can see the light, the stronger stuff is going right through. So parallel lines straight through. And you'll notice when it hits the curvature, there's a refraction and it bends. And look at this focal point right here. So there you go. Now, if you look at that, that's quite a decent curvature. That's stronger than the curvature in, say, my spectacles, which have a magnification of about 2.2, right? This one would be different, very different. The curvature is quite strong. And look, that means it focuses the image right there close to the lens, right? So you can change that situation. And we're just projecting light through there. Okay, what if I show you another one? Hopefully you can see this one as well. And what kind of lens is this? Converging. Sorry, oh, sinful me. It's biconcave, so it's diverging. Here's the light ray kit on the left, and you see the three parallel sets. Beautiful. This one's a really nice picture from the lab. I've got parallel lights, and as they hit the concave once, and then I refract through the plastic, very minimal effect on a thin lens, and then bang, look, it refracts outwards. Notice how the middle line in there and in here is undeflected. That's called the principal focal line. I'll say it again, principal focal line. So that runs straight through the middle in convex lenses, biconvex, and also biconcave. Principal focal line goes right through the middle, or principal focal axis. Okay, so you need to be able to appreciate the way lenses operate differently according to curvature, according to the refractive index of the glass or plastic, like those two lenses. And the third thing, remember, was the medium which you're refracting into. So air, silicon oil, or water. Okay, what if we zip back over to the whiteboard again? I want to show you one last thing before we wrap up. So moving down, isn't this exciting? What about angular magnification? So what if this time, instead of shining light through, I'm actually just going to actually have an image. So this is very much the stuff of using spectacles or telescopes or binoculars, right? I actually have an image or an object at one side of the lens, and light comes, hits the object, and it reflects back off the object, you know, like light does. The reflected wavelengths push back off the light, bounce off, and they come back this time through a lens. Now, funnily enough, you might think of it using only through spectacles or binoculars, but if you think about it, this is exactly how you see. This is actually what your eye does. You have a small, very fluid, gooey, see-through lens in each of your eyes. So without this lens capacity to focus and bring images in towards the back of our eye socket in our head, like this, there wouldn't be any seeing. But remarkably, our body can affect these lenses, and the little lenses have small muscles attached, and pardon me, our body is actually able to squish and lengthen the lens and literally change its principal focal axis. We can change its focal length. It can manipulate all that just by muscles, and all you'd have to think is say, oh, look in the distance, and your eye will stretch the lens just instinctively, automatically, in response to your brain signals. And then what do you know? You've got a longer focal length. Let's look at an example though. How does it work? Okay, so a lens, I've got an object that's showing in a biconvex lens. Now in a standard biconvex, which is normal for magnification, have a look. I've got the principal focus, so principal focal line through the middle of focal axis with the little F's on it. And notice that I've got an F distance as well. So I've got a focal length for the object. So imagine this is a little, I don't know, candle or a stick or something, standing there in front of the lens, and it's this many meters away. The O, object focal length, is there. But also, I form an image. As the light comes through here, I form an image through the lens, and I have a focal length of the image away from the lens. Do you notice what I and O, how they're different? Notice how this one is only going to here, but this one is going all the way over to there. The image focal length, the focal length of the image is actually greater than the focal length of the object. So we know that means it's going to magnify the object, and lo and behold, look at the shape of the image down there. It's actually upside down, it's inverted, but it's larger. It's actually larger. How do you tell how much larger? Again, I really don't know what chance you have of getting this in a question, but let's work out how to do it. Here's your linear magnification formula. Now, let's pretend the length of that image was H, or the height of it. H prime, or H apostrophe there, is the image formed by the lens, and H is the original. So linear magnification is just the size of the image formed, H prime, divided by the height of the real image, the actual image. Linear magnification, so there it is. It includes a negative sign. That is just to give us a little physics correction. It reminds us that, remember, as the images come through here, light passes through the middle of the focal line there, but light from the top goes to the bottom and light from the bottom goes to the top. In other words, we form an inverted image. Your eye receives everything upside down, but your brain has an algorithm in its nerves to flip the image for your brain to understand. But you're actually seeing, look across at this screen right now, you're actually seeing this laptop upside down in the back of your eye, but your brain gets to it before you've got a chance to get dizzy. If the image is virtual then, so if the image has been formed in front of the lens, remember the image distance will be negative, right? It's negative because it's forming, you trace the rays back, it's forming in front of the lens, not behind it. And that means the magnification will get positive for the erect image. So it's negative for inverted images, positive magnification for a right side up image, or the unfortunately named erect image. Okay, what about 2 practice questions? You up for that? Of course you are. You're up for anything, right? Sample problem number 1, have a look. What does it say? Right. Convex lens has a focal length of 10 centimeters. A little candle is placed in front of the lens, 16 centimeters away, but it's in front. Work back with a ruler and pencil to use ray tracing to determine what location the image will be in, the size of it, and the orientation. So the image of the candle that a certain lens will form, it's convex, right? So biconvex is what we mean there. Okay, so here you go, biconvex lens. The technique you use is called ray tracing. So this is what's happened exactly here. Here's what ray tracing means. You show the following features of the light ray as it interacts with the object. So here's your little candle. You see it there? So I can draw it on for you. It's that little blue arrow. That's a candle. Should be a flame up the top probably. That's the candle. The image is down here. Okay? Image is way down there. Right? So we've got 3 things to draw. From the top, if I take from the top there a middle, I've got 3 rays to draw. I've got to draw the principal axis, which is this one, right through the middle, down to there. I've also got 2 focal points. So it's going to be over here. Right? And you'll see the way the objects have been done. The 3 rays, I've got one passing through the center of the lens. Sorry, that's the one I just drew then. That's 1 ray. Then there's one parallel to the principal axis, which is this thing here. Right, so across to there, see, I draw it across to the center of the lens, and then from there down. And then I've got another one over here, passing through the focus. The focus is down there. So okay, down there, focus of the lens. Remember, because this image, this candle is in front of the lens. Sorry, not the image. The image is behind the lens. And we draw it across. That's where it converges. And so there it is. I've got all of those things. Now, if you used your ruler and drew those lines to get this little image worked out, you'll notice that the bottom of that image there became the top on this image side, and the top became the bottom down there. And if you used your scale exactly right and measured correctly, the image that I traced out will be 27 centimeters away on the other side of the lens. So it's actually a real image. That's how we know it's real, because it's on the other side of the lens. 27 centimeters away, and it will be 15 centimeters tall upside down. That is inverted compared to the direction of the candle. Okay, want to try one more? Of course you do. All right, let's have a look. Let's have a little look. Sample problem number 2. The candle gets moved, same candle, but it's actually 5 centimeters in front of the same lens. Now use ray tracing to determine the location, size, etc. Details about the image. Now this is different. Before Before, we were further away in front of the lens. But if you put it too close in front of the lens, too close here, it's different this time because I could actually be forming myself a virtual image. It's the same lens, but there's my little convex lens. Okay, now there's my object in front of the lens. Now, this time, I'm going to have a different scenario. So I've got my image going through here. I won't draw all over this one. This is the object, right? Now, if I drew through over to here, these rays are converging, you'll notice. I'll draw them across over here. They don't, sorry, I'm so sorry. I keep saying the wrong word. They are diverging, not converging, diverging. That is, they're pulling away and they don't all settle into one focus spot. So you know you're not going to deal with a real image. You're going to form one back here, which is traced back from these things. You're going to do backwards tracing. Do you see the little dotted lines again? So you trace back and you're going to have a virtual image. So you draw your lines. 1, 2. This one's parallel to the principal focus. Okay. I've got that one there through the middle. So yes, I've got to leave that principal focus. Actually, I might make that one a different color. Principal focus through there, right? I keep that principal focus on there. That's the bottom of the image. That one stays. Principal focus, principal focus, focal line. But for the rest, I've got all my rays diverging out. So now what I do is I trace them back with dotted lines. 1. Do you see what I'm doing? I'm forming where the image will go. And this one's through the center of the lens. That just goes straight up. So there I go. And what I'm actually going to do is form an image on the bottom of the focal line there. And look at that. These lines all converge at that one spot. But notice it's the right way up this time. Yeah, I make a little arrow there. Sorry, it's a bit messy. But how do we describe our solution this time then? Well, we describe it like this. The image of the candle will be 10 centimeters away on the same side of the lens. It will be 20 centimeters tall and it's not inverted, it's upright. And key thing here, it's a virtual image. See, I traced back these actual rays of light. So the lens is actually able to focus a little image from out of the glass, but it's virtual. It's not real. Your eye doesn't see it on the same side of the lens actually, but the diverged light forms this second image back here on the same side of the lens. And remember, virtual images are not inverted and they're on the same side of the lens. 20 centimeters tall. So interesting, isn't it? The image of the candle. How tall was the candle exactly? Did we have it originally? There we go. The candle is 10 centimeters tall. So we could do a little magnification on that too. Remember how you do that? Candle was 10 centimeters tall. So height of the candle, 0.10 meters. And here, I've actually found out that the candle is 20 centimeters tall. So H prime is 0.20 meters. And I think you all see where I'm going. Magnification. You don't even need maths for it, but remember in physics, we like you to show your maths. So it's H prime divided by H. That is the length of the formed image divided by the original real length. Okay, you got it. You probably saw this long before we wrote it down. 0.2 divided by 0.1 equals 2 times. So that's the magnification, or a nice little optometrist would say that's lens has a diopters, a power of the power of 2 diopters. That's how he would, the language he would use. Okay. So that's all we need. So if you take a close look down on there, sorry, the bottom of this whiteboard, I'll make this whiteboard available to you via a link, so you want to have a check it out. Don't forget, main things to remember, biconcave lenses diverge in and out, and light spreads goes in and spreads out, except that through the middle, it always continues. Same as this, through the middle of this biconvex lens, the principal focus, light is undeviated, it's straight, but everywhere else, it actually goes, refracts in, and they will focus at a point there. With our diverging lenses, remember, what is the trick I showed you? Remember the trick, remember the trick. To find the image being formed by, oh, we've gone way too. The image we've formed with a diverging lens. Remember, you're going to be using ray tracing to go backwards. I'll use the rainbow pen. And here are these images up here, right? So you would just trace them all back. I'm tracing these as straight as I can. These are like dotted ones, so dot, 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 dot. There. And they start to cross over now like this. And what you'll get is you'll form your image there. But it's not real, is it? It's virtual. It's a virtual image, and it's the right way up. Okay, take all of those into account. And I've got one more Christmas present for you. When you look at this video and you want to come and see the whiteboard, if you'd like to see the past paper question about about images in mirrors, not lenses, here is a past paper question for you from one of the preliminary independent schools exams. So you can see that when I talked about reflections in the image, the images formed in a convex and a concave mirror, namely a spoon. So have a look at that. Keep looking around for lens questions. You got to be lucky to find one, but you never know. Okay, everybody. I really hope you're having a good week this week at school. Hope you watch this video. Make sure that you come through this, because I need you to be finished it and moving on. By the time I start again in week 2, we'll be zipping into thermodynamics and riffing through to the end of this topic. All right. Hope you're having a good holiday. Stay safe and wash your hands.